Good evening, all. Welcome to the week 8 of the. Welcome to the week 8 of the problem solving session for the course Geotechnical Engineering 1, handled by Professor D.N. Singh of Department of Civil Engineering of IIT Bombay. So, I am Yogendra Narayanan. I am a PMRF research scholar. We'll be conducting these sessions every week on Saturdays 5 p.m. to 7 p.m. And since this the attendees might be new every week. So, in order to give a brief uh, preface of why these sessions have been conducted is to make this uh, is necessary. Hence, the, so since this mm, s- s- since these sessions are conducted every week and it is also available in public forum, so I would like to repeat or reiterate the necessity of this, the purpose of this session. This session is primarily dedicated to make the learners proficient in understanding the concepts and making the learners familiar with, more familiarized with the problems uh, corresponding to the contents that has been covered in the uh, corres- particular week, and this continues for every week since it is a 12-week course. And uh, prim- basically we will be solving some of the previous assignment problems and other questions uh, from the uh, from the contents that has been covered in the particular week, and to make the learners familiar in approaching the problem using the right procedure, and uh, which will which will in turn enhance the concept clarity. And coming to this week, this is the week 8 of this lecture of this course, in which I would like to give a brief account of what has been covered in this week. So essentially, this week started with the problem of two-phase flow. Sorry, two directional, two-dimensional flow, which is essentially flow nets, and the concepts of flow through uh, the basement, that is the foundations of the dam, and the construction of flow nets, the assumption of flow nets, how Darcy's law has been extended to apply for two-dimensional flow, the partial differential equations governing these flow, which is essentially Laplace continuity continuity equation, followed by uh, flow through earthen dams, phreatic line, and equipotential lines and flow lines, various boundary conditions, and finally uh, it has been uh, extended to anisotropy, permeability, anisotropy, flow anisotropy, in which the Laplace equation has been extended for permeability and isotropy. And furthermore, the corrections in the dimensions of flow nets and the uh, dam structure that has to be made in order to convert the uh, anisotropy to an isotropic system. So based on this, we have, uh, I think it is better to solve some problems, and through it we can understand the concepts even more clearer. Uh, Hope I'm audible, right?
Yes. Sir, it's audible.
Slides are visible.
Yes, sir.
Slides are visible, right?
Yes, sir.
Okay. So we'll be moving to the problems. So and also to mention here, we'll be solving one problem from the previous week, which serves as the connect to this week, so that uh, it will be useful in uh, understanding the flow through soils also, and how the various heads and potentials get uh, potentials vary uh, as the flow occurs. So we'll solve one problem which serves as the bridge between the last week and this week lectures. So this is the problem. These are the two conditions. Determine the heads at different points uh, and determine the direction of flow for the given conditions. So these are the two conditions. One is condition A might be, and this is condition B. So here we need to calculate for 3 points A, B, C, and D. So first we need to calculate the total heads at these points. So if we calculate total head, then we will be able to determine the direction of flow. So similarly for these cases also, uh, we can uh, determine the uh, nature of that is determine the heads same at this point, this point, and maybe uh, here also, not here, here maybe, right? Now let me give a brief uh, uh, how to approach these kind of problems. So first, it is always better to make a table. Uh, it is always better to make a table. So what is the condition? Uh, okay, there are two aspects in these questions. Heads at different points. Heads means it refers to total head. So how will you define the total head? Can you say?
Pressure head plus elevation head.
Yes, pressure head plus elevation head. Right. Now just make a table here. Uh, there are 4 points: A, B, C, and D. This is elevation head. This is pressure head. Here it is total head. Right. Now let us determine the heads at different point. So for first, for determining elevation head, we need to fix the datum. Let us consider this point as datum. Okay. Okay, now can you say the elevation head for A?
1900.
Yes. So these are all in millimeters. So if we write in meters, it will be 1.9 meters. So for B,
Uh, for B 1300, 1.3.
yes, 1.3.
3.
For C,
0.5.
0.5.
5.
And for D,
0.
0. Now, what will be the pressure head at A?
Pressure head 0.
0. At B?
0.6.
Yes, 0.6.
6.
At C?
1.4.
No, here, see, that is where the
No,
catch
no.
is.
See 0.5.
Which one?
0. At C pressure head at
Hmm.
0.5
It will be plus or minus?
minus
Minus 0.5.
0.5.
Why? Here, these 2 points, you can directly mention that pressure head by keeping a by measuring the water column, right? Here, when you place a piezometer here, this point is exposed to atmosphere, right?
Yes, sir.
So if it is exposed to atmosphere, what will be the total head?
0.
It will be 0. So here total head will be 0. Now at point D, it will be obviously 0. Now you calculate the pressure total head now. Here it will be 1.9. Here it will be 1.9. Here it will be 0. Right?
Yes, sir.
Now there is an interesting observation here. Please listen carefully here. So when you take A and B, is there a flow of water?
No.
Because total head is 0. That means this is entirely the water column, which is not at all where flow does not take place within this. And if you consider CD, is there any flow?
No, no. Total head
So
added difference is
total
0.
head difference is 0. So now if from A to B there is no flow, and from C to D there is no flow. Now there is a flow from B to C. There is a difference in total head. So in which direction it has to flow?
B to C.
B to C.
Up.
Why? Because this
Downward.
has
Higher
total
head than.
higher head than this one. So the direction of flow will be downwards, right?
Yes. Yes, sir.
So can you do the same for B condition?
Yes, sir. Right.
You take the same as datum.
Okay, sir. At A,
Uh-huh.
uh, at the head elevation datum line is same.
Okay.
Okay. At A, pressure head is 0.
Okay.
At B, elevation head is 1.3.
5, 8. How are you saying elevation head will be same? Here elevation head is different, right?
Okay, okay, sorry, 400. Okay, 12 plus
It will be
1.7.
1.7. Now at B,
1.3.
1.3.
At C 0.5.
At C it is 0.5,
D 0.
0. Pressure head,
Pressure head at A 0. Pressure
mm,
head at B 0.4.
0.4,
And pressure head at C minus 0. Water table is pressure head is
mm.
okay total 615. Okay. 2.35. No, how to
Okay,
pressure
now
head.
see, now what you have to do is now you have to keep the piezometer here at this
Is
point. To what level it will rise?
6.5.
How much?
6.5 pressure head. No, no, total head difference. 6.5.
See,
Okay.
let me explain.
Okay, so
If you
tell me.
keep, ah, are you trying?
Explain, sir.
Okay, now if you keep a piezometer here, to what height it will rise? It will rise up to this point, right? Let us say point E. Are you able to understand?
Yes, sir.
Now, whatever this up to here, entirely this part and this part will get cancelled. So the remaining height will be this much. What will be the height here?
Why, sir? Cancel.
See, here it will be, if you keep earlier what we did here, it will be negative and here it is rising. So if you keep here, it will tend to increase towards the atmospheric pressure, which is this part. So the extra pressure will be this part.
Okay.
Okay, now the pressure head will be what here? The head, the line I have marked with arrow mark.
Okay.
All right.
Okay.
So
2.5.
8, 2.5.
1400 plus 650.
No, no.
2050.
From C you calculate.
Okay.
C, it will be 800 plus 400 plus 6.5. 8 plus 4, 12, 1.2,
1200. Okay. 1.2.
1.85.
Okay.
Right. So at D,
At a deep pressure head is total 8, 4,
it will add
12,
this also.
5, 17. 17 plus 2350 into 2.35.
Yes, 2.35. Now calculate the total head. It is 1.7. It is 1.7. It is 2.35. It is 2.35. Right?
Yes, sir.
Now, same way you analyze this point A to B. There is there is no flow, right?
Sir.
So from A to B there is no flow. And similar way from C to D there is no flow. But what about flow between B and C?
Head difference is there. So flow is upward direction C to B.
Yes, upward direction C to B.
B.
So what is the head difference?
0.65.
0.65. So this is the same here. Are you able to see here?
Yes, sir.
So one of the very easy method to analyze this is you have to check the water level between these two levels, right? And similar way here also you can see at A it is 1.9, at D it is 0. So the total head loss will be 1.9.
Yes, sir.
So the total head loss, head difference will be the difference in the water level in both the uh, both upstream and downstream. So this is the upstream condition. In this case, it is the upstream. This is the downstream. In this case, this is the upstream. This is the downstream. Right.
Yes, sir.
Now here I can say one analogy here. So this type of system where we will find in real life, not only in soil mechanics, real life situation.
Pumping in downward.
See, you have been to hospitals, right?
What, sir?
Hospitals.
Yes, sir.
So have you seen people getting syringe? That is saline
Yes, sir.
drips. So where will they place the saline container? See, this is the here is
Upper. Okay.
here is the patient lying. So from here, where will they place the uh, sal that is the trips container?
Upper.
They will place here and they will connect here. So it is the same way that is transferred here. When you take this up and up even more higher, the flow will be even more higher than higher in this direction. Now you imagine this is the human body and this is the uh, saline container. So the it will be kept at a certain height such that there is a smooth flow of liquid or whatever the uh, saline liquid into the human body. If you bring this container down, blood will start flowing through it. All right.
Okay, sir.
So this is how we can find this in very real life situation. We might have seen in several cases either in real life or in indirectly in movies, but we don't wonder why they are keeping it at a height. So this is the reason why they are keeping it. So hope I am clear now.
Yes, sir. Clear.
Now here what you can do here is, so take a random point here. Okay, so let us
Okay,
take
sir.
it is uh, it is 400 mm. This is 400. So let this point be taken as P. Calculate the effective stress here.
Okay.
So take the uh, density as uh, gamma sat as some 19 kilonewton per meter cube.
I think 9 meters.
How did you calculate? 19 into 0.4. This is the total stress minus. How did you calculate?
At vertical stress, so gamma into h, where h is equals to 1 meter, I think. 400 plus 600.
See, here it is water column, right? Where gamma will come here. Okay,
Okay.
water pressure you are saying.
Yeah,
Hello? Hello?
uh,
Okay. Now what will be the total stress here? Uh, it will be uh,
calci.
how much? It will be you take gamma W as 10, 10
Yes, sir.
into
0.4 into 19 plus 0.6 into 10.
yes.
Total stress minus
Yes.
1 into 10. Pore water pressure.
Here you have
To
made a
get the
mistake here.
stress.
Here it will be
Okay.
valid only when the water table is static.
Okay.
Now water is moving, right?
Okay.
So the point here is gamma W, pore water pressure is always gamma W into pressure head.
Yes, sir.
So in this case, how will you calculate pressure head?
Sir, I don't know, sir, but pressure at water table is at A, so rise to A.
Okay.
No.
Mhm. Now, now you have to follow this method here,
Okay.
right? Now, what will be the elevation head here? 1 point,
At
uh,
B 1.3.
1.3, and here the total head is 1.9,
9.
right? Now, here it is 0,
Yes, sir.
right? Now, at middle, what will be the total head?
Middle. Okay.
0.95, right?
100 plus 600, 100. Sir, at P, what is the pressure head, sir?
At B,
At P,
this point, na.
yes, sir.
So
What is
first you, uh, so the datum head will be how much here? It will be uh,
0.9?
0.9,
9.
right? Now, uh, what will be the pressure head here? It will be uh, so see now let me explain why the point is not right. So if you take 400 here, if you calculate by the how to put the conventional method, what you have calculated. Hello,
Tell me.
hello.
Yes, sir, visible.
So here, what will be the conventional method? It will be 4 plus 6, 1. It will be elevation height plus 1. It will be 1.9.
Yes, sir.
At point P also it will be 1.9. At point B also it will be 1.9. How flow will take place here,
Oh, okay. At the
right?
difference is no flow is not there, but flow is
Flow is
downward
there.
direction.
Flow is there.
Yes.
So the pressure head you have calculated is not the correct pressure head.
Correct. Okay.
So how you will calculate pressure head is you have to calculate the total head at this point and you have to subtract the elevation head.
Okay.
All right.
Ah, sir, tell me, sir.
Now here it will be 1.9. Right. Now 1.9 to 0, it is getting divided, it is over a length of zero point 0.8 meters. Right.
What is the 0.8, sir?
This one length,
Okay, okay.
this head loss is getting distributed by zero point 0.8 meters.
Okay.
So what will be the head loss per meter? You say this. So
Yes, sir. Wait, wait.
how much will be the uh, head loss per unit length? It will be 2.375 meters. Now, from if it is 1 meter, the head loss will be 2.375. So, flow is taking place from here. So, here up to this point, what will be the total head at this point? So, 1.9 minus 2.375 into 0.4. will be 1.9 minus 0.95. Hello?
Yes, sir.
Are you able to get it?
Yes, sir. 0.95
0.95.
meters.
All right. So
Yes.
meters. Now what will be the elevation head? It is 0.9.
Yes, sir. Point 0.9.
Now you subtract it, you will get 0.05. This will be the pressure head at that point. Now you multiply it by gamma W, that is 10. You will get zero point 0.5 kPa. That is the pore water pressure. Now you can subtract the total minus this. Are you able to understand? Hello? Are you able to understand now?
Yes, sir.
Are you clear or you have some confusions?
Sir, once explain the here 0.95 meters is the total head or head difference. Head
At
difference.
it is the total head.
So H is equals to I into L. So the in that formula I is equal to H by H is the head
H is
difference.
the head loss. Head loss.
Head loss.
Hmm.
మరి why it is 0.95 into some అంటే total head minus pressure L sorry total
Elevation head.
elevation head. But here
Yes.
H is the head difference.
No, no, no. See here. You have confused yourself. So what happens is here incidentally total head and head loss is same by chance. So see here the only point is uh, here what is the total head here? What is the total head at B? If you respond only I can move ahead now.
Sir, more next question, sir.
No, no. I'm just trying to explain once again. So
Okay,
what is
okay.
it? What is the total head at B? It is 1.9.
Yes, sir.
What is the total head at C? It is 0.
0.
So within the soil sample, that head is changing to 1.9 to 0.
Yes, sir.
So that is happening for a length of 800 mm.
Yes, sir.
That is zero point 0.8 meters.
Mm.
So what will be the here again one more point is this head loss is 1.9, right? Hello?
Okay.
Hello? Hello?
Yes, sir. Hello.
Head loss is 1.9.
Yes, sir.
So what will be the head loss per meter? You have to divide 1.9 by this length.
Yes, sir.
This is I, hydraulic
Yes,
gradient.
sir.
All right. Now
Okay.
you have to calculate total head at this point.
Okay.
Now here that means the total head is reducing from 1.9 to some value,
To 0.95. Mm.
0.95. So how will you calculate
Yes,
1.9 to, this is the head loss that is taking place in this direction
yes,
up to
sir.
this length. So you have to multiply this. You have to subtract from total head the head loss. So you will get the total head at this point. You know the elevation head. You subtract the elevation head from total head. You will get the pressure head. You, if you multiply gamma w, you will get 0.5. Right?
Okay, sir.
So this concept you please remember. We will solve one more question in the similar fashion very shortly.
Yes, sir.
All right. So always remember, uh, pore water pressure is always unit weight of water into pressure head. Right? You cannot. I think I explained why you cannot directly multiply the height of uh, water column. Are you clear now?
Yes, sir.
Okay. Now let us move to the next question. So there is a reason why I have included this question. So shortly you will be realizing why I have included. So now you can come to this question. A flow net can be utilized for determining uh, what are all the parameters: seepage pressure, exit gradients, seepage, that is discharge, seepage discharge, and hydrostatic pressure. Here you can, this is not hydrostatic, it is pore water pressure. That is obviously hydrostatic or pore water pressure.
Think exit gradient.
See, flow net is, consider a dam here. Here, this is the upstream, this is the downstream. You are constructing several flow nets. So, what are all the quantities you can determine?
Seepage quantity.
Yes, that is obvious. As you said already, exit gradient also can be determined if you know the dimension of the exit uh, flow, that is flow channel, right?
Hmm.
And you can also determine seepage pressure. Seepage pressure is I into gamma W. I you can determine with every equipotential point, equipotential drop, you can determine I. So seepage pressure also you can determine. If you determine seepage pressure, obviously hydrostatic pressure, we know you will be calculating the total head at this point and this point. You will be subtracting it, and you will subtract the elevation head. You will get the head difference. Uh, Subtracting the elevation head, you will get the pressure head, and obviously you can calculate hydrostatic pressure, which is pore pressure. Are you able to understand?
Yes, sir.
Are you able to understand this?
Yes, sir. Seepage pressure is also determined, sir.
Yes. So you have this relation, na, I gamma W, I into gamma W,
Yes, sir.
which is seepage pressure per unit volume.
Okay.
So I how will you determine? So you will determine, for this is a equipotential line. This is an equipotential line. So you will determine what is the head loss between these two, and divided by this length, you will get the I value.
Hydraulic gradient.
So that is how flow net is used in two-dimensional flow to get the hydraulic gradient. If you get hydraulic gradient, everything you can get. Seepage discharge you can get, Exit gradient you can get, seepage pressure you can get, and pore pressure you can get.
Hydrostatic pressure, pore pressure. Okay.
Hmm. So you can determine all the quantities. But now you you can answer this question. During seepage through a soil, direction of seepage is always parallel to equipotential line, perpendicular to streamlines, perpendicular to equipotential line, none of the above.
Perpendicular to equipotential lines.
Yes, it is always perpendicular to equipotential line. So moving to the next question. Why sheet piles are provided and which is the preferred position? So you have a dam here which is having a downstream end water table, upstream end water table, and you have to provide you have to mention why sheet piles can be provided and where to be provided.
Um, Downstream,
Why downstream?
because water flow up to down,
Okay.
so that's why. How to tell?
Now uh, here you have to consider two important points. Now let us consider two important situations. So one is with sheet piles and second is without sheet piles. Right?
Yes, sir.
Now it will be the flow net like this. So it will be like this. Right?
Yes, sir.
Now you remember we calculated pore pressure here.
Yes, sir.
Similar way, can you calculate pore pressure at each and every point? I am not saying to calculate now. Can we calculate or not?
Yes, sir. Can we
So
calculate?
that means there is an pore pressure acts equally in all direction. So there will be a uplift force here,
Yes, sir.
right? So uplift force depends upon what? I,
Oh, yes, sir. Hydraulic gradient.
because we calculated H minus delta I into delta H.
What?
See, the total pressure acting on this point is directly proportional to I.
Okay.
So the main motto of providing sheet piles is to reduce this I.
Yes, sir.
So how I is defined? Delta H by
L.
L. You cannot reduce this.
We reduce. So we increase the seepage length. So exit hydraulic gradient is decreases.
Yes. So you increase the seepage length. That
Yes.
you have to prevent the uplift force in this entire region.
See
So where will you insert sheet piles?
downstream.
See,
Mm.
here if you install a downstream, how it will decrease the uplift pressure?
Okay. So mm,
It might prevent to an extent piping, but
yes.
what about uplift? So always sheet piles are provided here. Now what will happen? Water has to flow in this manner,
Okay.
right?
Yes, sir.
It has to come through like this. So during this, it will lose much of its energy.
Okay. Seepage
Now,
pressure is reduces.
this is how uh,
Force reduces.
you increase the L. Are you able? Are you understanding?
Yes, sir. Understood.
Now, if you consider without sheet pile, L is relatively smaller, and if you provide sheet pile, it has to travel this entire length, which is an increase in length. You are increasing L,
Yes, sir.
so I has to decrease. If I decreases, obviously uplift pressure will decrease.
Yes, sir.
So always sheet piles are given in upstream and to decrease the
Increase the uplift force and
uplift
exit
force and
gradient.
exit gradient. And usually people what they will do is to prevent to be in a safer side, they will they will install sheet piles in both upstream and downstream also.
ఈ వాటర్ టేబుల్ దగ్గర కూడా సీక్వెన్స్ పెడతారు. Sir,
Yes.
if water table is at the right hand side water table,
Flow
so
nothing.
sometimes that is anchors or seat piles, sir. Uh,
These
at
are
the
sheet
down.
piles.
Not that, sir.
Hmm.
Uh, eh, how to ask? Yeah, that.
Hello.
Sir,
Uh-huh.
some in the lecturers are at the right hand side water table. Some anchors are
Those are filters,
okay. Not seat piles, sir.
not sheet piles. They are filters.
Okay, okay, sir.
So let us. I will come to that only. Next question is on filters only.
Okay, okay, sir. Thank you.
So this is one case of here the dam might be pervious or impervious. It might be made of concrete, which is completely impervious, or it might be made of it may be made of soil, which is pervious. So now let me come to this part. Where do filters are placed in a dam? Here it is particularly not only in a dam, and why are they provided? So you have a dam here. Where will you provide the filter?
So filters are downstream.
It will be in downstream, right? So what does these filters do?
Reduce the uplift force. Mm.
They will reduce the
Piping
yes, they will reduce the exit gradient.
is a pipe. Mm,
They will reduce the exit gradient,
exit.
which is responsible for piping,
It's a,
right? Why they will reduce the exit gradient? So filters are essentially exposed to atmosphere.
it's a,
So if it is an atmospheric condition, water will start flowing and they are highly pervious.
okay.
So there will not be a piping failure, which will proceed like this. Piping is essentially eroding,
Erosion of soil.
right? Now, if you place a filter layer, you will be uh, exerting a higher weight also, which will prevent the erosion, as well as the exit gradient also will be reduced.
Okay.
So this is always filters are always to prevent piping. And one more thing is if flow occurs through the dam, you know this phreatic line, right? It will come like this.
Yes, sir.
Now, if you don't place filter inside, that is protruding inside the dam, this phreatic line will come and hit here.
So dam was failing.
So the downstream end it will completely fail. So what they will do is they will insert two, three types of filters are there. One is here they will place heavy, highly pervious boulders, rocks, so which is essentially exposed to atmosphere. So the flow line will come and hit right here. So it will not affect the downstream end.
Okay.
So that is why filters are provided. This is also a type of piping failure. So that is why filters are provided at the downstream end to prevent piping,
Okay.
right? So option C is right. Are you clear now?
Yes, sir. Clear.
Now let us move to the next question. Upstream slope of an earthen dam during steady seepage condition is.
Upstream slope.
This is the earthen dam.
Okay. Theoretic
You
line.
consider this as,
Water table.
here it is. This is upstream. This is downstream.
Downstream.
What is upstream slope? This is the upstream slope.
Yes, sir.
So this upstream slope is a what type of line? Whether it is equipotential, it is a flow line, it is a phreatic line, or it is a seepage line.
I think water is not allowed. Flow line.
Does flow occurs through this? See, this is pervious.
Okay.
Are you getting any idea, or can I explain?
Explain, sir.
See, now I think this Sir has discussed in the lectures also. You can revisit this once. See, now you just draw the phreatic line here. It will be like this.
Like, okay.
You have a filter here. It will be like this, right? Are you able to remember or not?
Yes, sir.
So this is the flow line. Okay.
Okay, sir.
Now how this flow line is? It is perpendicular to the slope.
Yes, sir.
So which line is perpendicular to the flow line?
Equipotential line.
Equipotential line. And one more thing. This is one argument. Second argument. Second argument to why it is equipotential line. You keep a piezometer here.
Okay.
To
A
what?
total head is same in at every point.
Total head is same at every
Same
point.
point.
So which is the characteristic of an equipotential line.
Okay, sir.
So it is always an equipotential line. Okay.
Okay, sir. Understood.
Now same thing applies to downstream slope also. Now what about this point? Bottom.
Equipotential line.
How?
At a total difference is same at every point.
How total head is same here? See here it is
So,
same. See there is a flow like this. There is a flow like this. And these are the, this is the flow net.
yes, sir.
Now you will consider this as equipotential or flow. See, water is entering into the dam from all the directions like this.
Yes, sir.
perpendicular to this line. Okay,
Okay, sir.
and water is reaching here. Okay, at the downstream end. Now water flows through this flow nets like this. Okay,
Okay, sir.
are you able to understand?
Yes, sir. Understood.
Now similar way water will also flow like this at the interface, right?
Yes, sir.
So always this line is the bottommost flow line. Okay,
Okay.
this will be a equipotential line. It will be a bottommost flow line.
Okay, sir.
Okay,
Okay, sir.
now you can ask one question.
Sir, the video is stuck, sir.
Hello,
Yes, sir.
now you can ask one question here.
Okay, sir.
I said this is an equipotential line and this is a flow line, right?
Okay, sir. At just above the line is flow line, but that line is equipotational line.
See, uh, just a minute. So let me use this. See, this is the equipotential line.
Equipotational line.
This is the flow line. Now, are you able to understand?
Yes, sir.
Now, what is the condition for equipotential and flow line?
Perpendicular.
Are they perpendicular here?
No, sir. Ah, yes.
So, so what does it mean? So this is a anomalous point.
Enamel.
Okay. So where this does not obey. So also we will call this as point of singularity.
Okay, sir.
Okay. So you can make note of it. It is just uh, to give you an information to you.
But in lecturers all told that line is equipotential line.
This is equipotential only, no doubt. And this is
Okay.
also seepage line, flow line.
So both are, sir.
This one, horizontal one.
Okay.
See, horizontal one is a flow line.
Yes, sir.
This is an equipotential line.
Yes, sir.
Are they perpendicular?
No, sir.
So that is why this condition is a is a singularity condition.
Okay.
So
So
it
now the
deviate it is just it deviates from the assumptions that is made.
okay. Okay, sir.
Okay, so you have to keep in mind this point.
Okay. Okay, sir.
Okay, so just to give you this thought only, I said this.
So now we consider horizontal line is equipotential line.
No, no, no.
But in lecturers are told that the horizontal line is equipotential line in lecture
Okay, okay. Just a minute. Just a minute. Just a minute. See here.
in
Just a minute. Let me say. So let me check once.
okay, sir.
So here it is there. So you have a downstream filter, and this is like this. And you have like this. And this like this. And Okay, 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 okay. There is a mistake here. So this is also an equipotential line only. Hello?
Yes, sir.
This is also an equipotential line. This is also equipotential line. This is also equipotential line.
Okay, sir.
Okay. So please correct it. Uh, and uh, but this upstream slope is always an equipotential line. That is the question here.
Equal protection. Okay,
So
sir.
make a note of it. And moving to the next question, which of these
Okay,
statements
sir.
are correct? To prevent the possibility of erosion and piping, following approaches could be used. Hello?
Yes, sir.
Can you answer this question?
Okay, providing cutoff wall, vertical cutoff wall at
Cutoff wall
upstream
is
side, I
just a
think.
sheet pipe.
Okay, upstream side. So this is a downstream side. It is wrong. Providing impervious blanket, providing protective filters. Providing protective filters.
Okay, that is right. Providing protective filters is right. And also
Impervious blanket.
providing impervious blankets is also right. Because as I said before, by placing this thing here, impervious blankets also, you will be preventing the, you will be sustaining the force exerted by the exit gradient.
Okay,
Force
sir.
exerted by water at the point of exit, right?
Impervious blanket is
Impervious blanket is
also put at
essentially
the
made of similar to concrete.
upstream side.
No, no, impervious blanket is also provided at the downstream only.
Okay.
Okay, these are two different schemes that can be undertaken.
Downstream,
These both are in
sir, not
downstream only.
upstream.
These are both at downstreams only.
Okay, sir.
These are both at downstream only.
Okay, sir.
Only sheet piles you will be
Okay,
providing at
sir.
the upstream end.
Okay, sir.
Okay, let's move to the next question.
Okay, sir.
Now, this is a fairly simple question. Equipotential lines and flow lines intersect each other at
Right angle.
right angle. So, what will happen if the hydraulic gradient is this is exit? Exit hydraulic gradient is less than critical hydraulic gradient of the porous media is soil.
Okay.
How will you answer this question?
Exit gradient is less than the critical hydraulic gradient, so it's safe.
It is
In case critical safe
it is
and
safe, right?
no,
It is right.
yes,
What you
sir.
said is right. How will you determine quantitatively? You will be determining by factor of safety, which is
Safety,
IC by I. So
which is 2.
when I becomes greater than IC, FOS becomes less than what will happen to FOS? If for I greater than IC, what will happen to factor of safety? Hello?
Yes, sir.
If I is greater than
I,
IC, what will happen to factor of safety?
I don't think so.
It will
One
be
more than one.
less than 1.
Okay, okay.
See, denominator is more than numerator means FOS is less than 1.
Okay.
So that means if FOS is less than 1, then piping will be occurring. So, but the given question is I is less than IC, which implies FOS is greater than 1, which renders the structure safe. So the option will be
Greater
none
than
of the
one.
above. Okay?
Yes, sir.
Are you able to understand or not?
Okay, sir.
Okay, let us move to the next question. So
Yes, sir.
this,
Understood.
okay, is there a
The
lag?
critical hydraulic gradient is greater than. Okay, okay, sir.
Okay. So now answer this question. This is fairly simple question. So what will be the discharge per unit length if number of flow lines and number of drops are 12 and 10 respectively? Assume
Okay,
hydraulic
sir.
conductivity to be 1.5 into 10 power minus 4 and total head to be 5.
Number of flow lines. 12. Okay, sir. I will do. Sir, where number of drops and number of equipotential both are same?
Yes, yes. This if it is drops, na, it is always equipotential drops.
Okay, sir. Okay, sir.
Okay.
Nine into 10 to the power of minus 4 centimeter per second.
Okay. How did you calculate? Q is equal to K H
KH into NF by ND.
NF by
Number of flow lines by number of equipotential
ND.
lines.
So
The
it will be
drops.
1.5 into 10 power minus 4 into head will be 5 into 10 by 12. So how much will you be getting? 1.5 into 5 into 10 divided by 12. How much you will get? You have how much you got?
Sir, flow lines 12 and
Hmm.
so 12 by 10, sir.
Acha, acha, okay, okay. 12.
Okay.
Okay. Sorry, sorry. Hmm.
By 10.
Hmm.
So 9 into 10 to the power of minus 4.
Okay. Now here NF is flow lines or flow channels?
Okay. NF is flow channels.
Then we have given number of flow lines. How much will be the flow channel? You draw the flow net.
Okay, okay, wait, sir. Sir, flow channels -1.
Yes. So you
So
correct.
it is okay, sir.
It will be 11.
Okay, 5 into 11 into 1.5. So now 8.25.
Yes. So that is the answer.
Okay, sir.
8.25 into 10 power minus 4
-4 centimeter per second.
centimeter. Convert this. This is 5 meter, na? 10 power minus
Okay,
6 meter cube per
okay, okay,
second.
okay. 1.5 into 10 to the power of -6.
Centimeter meter cube per second. Right? Okay.
Okay, sir.
Hello. Uh, Now this problem is just an inverse. So you have head, you have ND, you have NF, you have Q. Now you calculate K. Okay? Hello.
Yes, sir.
So you solve this question now.
Okay, sir. 3 into 10 to the power of -5 meter per second.
Uh, It is just Q will be 0.00018 equal to K into 30 into 5 by 25. It will be 1, it will be 5, it will be 6. Yeah, obviously. How much did you get? 3 into 10 power
3 into 10
minus
to the
4
power of -5.
meter per second. This is the value. Okay, now let us move to the next question. So what is the this is just centimeter second.
Sir, in before problem, I have a doubt. Unit, sir,
Yes, yes.
where Q, where discharge is equals to meter cube per second, meter square per
Yeah,
second, sir. Meter cube per
meter
second.
cube.
Okay,
Mm,
but meter cube per second. Okay, so we meters. So now we calculate meter cube per second in equals to meter. So meter square per second. I get
yes.
meter square per second. So NF
Yes.
and ND.
Let me explain that. So it will be ideally speaking, it will be meter cube per meter square per second only.
Okay.
Now see, here it has we discharge unit is meter cube per second, right? Hello,
Second
meter cube per second
per meter length. So I think into
per
meter
meter.
into 1 meter. Yes, sir.
So
Okay,
let
sir.
just listen here. So it will be meter cube per second per meter,
Okay.
right?
So yes, sir.
Let me complete. Now here you generally people tend to do, you will cancel this meter and you will write as meter square per second.
Yes, sir.
But
Okay.
physically you should not do it. It will be meter cube per second per meter only. So and another thing is, here you will be multiplying with one meter length, unit length. So eventually it will be meter cube per second only,
Okay, okay, sir.
right? So you don't get confused here. You don't put the unit as meter square per second. It will be always meter cube per second per meter only.
Okay, sir.
Okay, you don't. It is not advisable to do like that. Okay, now let us move to the next question. So now you can solve this. I think we solved this. You solved this in previous week also. Hello, can we solve this?
Yes, sir. 6.
6 into 10 power minus 4 directly,
Yes, sir.
right? Now, what will be the answer for this
Yes.
one? Next question. Flow line makes
Next
angles
question.
A1 and A2 with the normal to the interface of the soil having permeabilities K1 and K2 before and after deflection. Select the appropriate relationships according to the law of deflection.
Okay. Balance.
So always draw the figure. So this is the interface. Here it is K1, here it is K2. Now flow line is hitting like this. It is deviating like this. Angle of incidence will be, you draw perpendicular to this line. This will be its angle A1. You draw perpendicular to this line. It will be A2. What is this? It is similar to Snell's law in optics.
Okay.
So K1 by K2 will be equal to tan A1 by tan A2. This is similar to Snell's law. You can go through the derivation in the lecture. So the option here will be this one. Okay. Hello. 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 Are you able to hear? Hello.
Yes, sir.
Are you able to understand?
Small network issue. Okay, sir.
Okay. So let us move to the next question. So quickly. So in a flow net, the length of the flow line in the last square is 2 meters, and the total head loss is 18 meter,
Okay, sir.
and the number of potential drops is 12, the value of exit gradient.
Okay.
So you just try to solve. I will be back in a minute.
Okay, okay, sir.
Have you tried to solve?
Sir, how to solve? I don't know, sir.
Okay.
The last
So
square is meter.
just I will no problem. Uh, so see, the total head loss is 18 meters. So
H is equals to 18 meters.
you consider earth dam.
Okay, last point is 18 అంటే 1, 2, 3, 4, 5, 6, 7, 8, 9.
So this is 18 meters, right?
Yes, sir.
Just this is the ground level, and when you reach here, there are 12 drops.
Yes, sir.
Now this is the flow net,
Mm.
This is the flow net, and maybe this will be the
Oh,
exit gradient.
okay.
So it will be like this, right?
Yes, sir.
So they are saying that that exit gradient is a square with length 2 meters.
Okay.
So that means this is the 11th equipotential line, and this is the 12th equipotential line.
Okay.
Now total head loss is 18. So per drop, how much is the head loss? 18 by 12. Hello.
Sir, what?
See,
So, why, sir, 18 by 12?
the total head loss is 18.
Yes, sir.
So that is happening. That is divided into 12. Are you understanding or not?
Not, sir.
See, just look at the figure. The total head loss is 18 meter,
Yes, sir.
and there are almost 12 equipotential drops.
Yes, sir.
So you have to calculate for the last exit gradient.
Yes, sir.
So that means you need to know delta H at this drop.
Yes, sir.
That means delta H at every drop will not change.
Same.
So how will you calculate 18 by 12?
Okay. If
Delta H by ND. Are you able to understand or not?
yes, sir.
Tell me clearly, you are able to understand or
Yes,
you?
sir. I understood.
Okay, now you will be getting 1.5.
1.5,
Okay,
sir.
okay. Now what is this meaning? See, listen carefully here. It is 18 meters. So
In every flow net, the drop is 1.5.
yes,
The,
exactly.
so, the total drop is 18.
Yes, exactly. Now let me. This is 36 meters height of water column. Just
Yes, sir.
assume. Okay.
Okay.
This is 18 meters.
Yes, sir.
Now the remaining is 18 meters.
Yes, sir.
So from 36, it is coming to 18 means there is a drop of 18.
Yes, sir.
That that drop we are just trying to divide by 12.
Yes, sir. Understood. Okay, sir.
That is the potential drop. That is what it means.
Okay, sir.
Okay. Now you got this point. Now I is fundamental definition of I is delta H by L.
Seepage length. Okay. In
Now
that box is 2.
2 1.5 by
2.
2.
0.75.
That is the exit gradient.
Okay, sir. Understood.
0.75 meter. See I na no unit.
Okay.
Okay.
Okay, sir.
Now next question will be fairly simple to you. You are a maths candidate. So if the equipotential function of for a flow is phi equal to 2x square y square plus 3, then what
Okay.
will be the component of flow velocity in x direction for the coordinates 2 comma 3?
Okay. Okay,
Can you
sir.
solve? What is the differential equation here? Rho phi by rho
Dou
x
plus.
equal to Vx.
Okay.
Now you need Vx. right? Velocity in x direction.
Yes, sir.
So you just divide, partially differentiate 5 by 5 with respect to x.
2x. So 4x y square
Hmm.
with coordinates x2,
Hmm.
y3 and 9, 14, 72.
72, right? Calculate for y.
Okay,
Here
sir.
in this case, dou phi by dou
Dou
y
y.
is equal to vy.
So 48.
Hmm. It is 48.
Yes, sir.
Okay.
Yes, sir.
Now, if it is a stream function, psi,
Okay.
same function is stream 2x square y square plus 3. What will be the flow
Same.
colors? It will not be same, because see, in case of potential function, dou phi by dou x is equal to vx, dou
Okay.
phi by dou
Dou y
y
equals
is
to
equal to
Vy.
vy. In case of psi, dou psi by dou
By
x,
dou x equals to Vy.
vy,
Y.
and dou psi by dou
By
y
dou y equals to Vx.
minus vx.
Okay, okay.
Okay, so you have to remember this.
Okay, sir.
So with this, now you can calculate for, in this case.
Which case, sir?
So you consider this as stream function,
Okay.
and now you calculate vx and vy.
Okay, sir. Okay, sir. Vy is equals to 72.
Mm-hmm.
Sorry, sir. Vy is equals to 72.
Mm.
Vx equals to minus 48.
Mm. Right. Okay. Are you able to understand now?
Yes, sir. Yes,
So
sir. Understood.
now you move to the next question. Calculate the seepage force acting on a road of width 7 meters and is under exit gradient of 2.
Okay, exit gradient.
What is known as seepage force? Seepage force per unit volume is I into gamma W.
That formulas are not told, sir.
Yes.
In lecture C4 force and F by V, that formulas.
Yes. Seepage force per unit volume is I gamma W. You
Okay.
have the length here into B. It will be force is, uh, how much you are getting here. You take gamma W as 10.
9.81 gamma W is 10. Okay. Where width is 7. Okay. Wait.
How much you are getting? Hello,
Yes, sir.
how much you are getting?
Sir, I have a small doubt. CPS force formula is equals to I into gamma W into CPS pressure into CPS area.
Yes. Here width only is 7, na? You can take areas into 1.
And the CPS pressure L.
See, hello.
Yes, sir.
See, seepage. Now, first you calculate seepage force per unit volume.
CPS force per unit volume. Okay, sir.
It will be 20.
Yes, sir. I into gamma 20.
Uh, Now you have into volume means it is obviously you length into breadth into height.
Okay.
You uh, you consider this as, if nothing is given, it is always meaning that it is unit length. So you have 7 here. L you can take as 1, H you can take as 1.
Okay.
Now you just calculate. It will be 140.
140
Yes.
meter cube.
Force unit is, it will be Newton or kilonewton.
Yes, sir.
Okay.
But
Now,
LBH meter.
hmm,
Okay. How, sir? High gamma W. Okay, sir. Kilonewtons.
hmm. Okay. Now let us
But
move.
sir,
Yes.
I have. Okay, sir.
Yes. Tell
Clear.
me.
The total 140 kilonewton is equals to CPS force.
Yes. Yes.
Okay.
Hmm.
Per unit volume or
Hmm.
not?
No. No. See, if it is uh, if nothing is given, you can take this as unit length.
Okay, sir.
Okay. So, but eventually, but dimensionally, it will give the value of this one.
Okay, sir.
But it is, as I said before, you should not say this as pressure. You will say this as kilonewton per unit meter into unit meter. Okay.
Okay, sir.
So let us move to the next question. So can you solve this question? First question.
Okay, sir. The Laplace equation of water flow in the porous medium which does not vary. It does not vary in boundary conditions. Okay, sir. I will try, sir.
Hmm. Hello. Hello.
Sir.
So, what is the equation here? Dou square h by dou x square plus dou square h by dou y square plus dou square h by dou z square equal to 0. Now what they have given is h does not vary in y and z direction. So this will be 0, this will be 0. So which will imply dou square h by dou x square is equal to 0. Okay. Now you have two boundary conditions. Now you have to integrate it. Dou h by dou x is equal to c1 and h is equal to c1x plus c2. Okay. Now h you know is at x equal to 0, h is 5 meters. So you substitute x is equal to 0, c1 will be 5. Now you know dou h by dh by dx is equal to -1. So c1 will be -1. So the equation for h is equal to -x plus 5. What will be the h at h at x equal to 2 is equal to -2 plus 5 will be 3 meters. Are you getting?
Sir, getting.
Okay.
Okay, sir.
Now you can try to solve this question. A sand
But,
deposit.
sir,
Yes, yes, yes.
how to take C1 is equals to 5?
We have this boundary condition, na? At
Okay, okay.
x
Oh,
equal.
so okay, okay. Sorry.
Uh,
Uh, okay, okay. Dou h by dou x equal to -1, C1 equal to minus. Okay, okay, sir.
hello, hello.
Sir,
Are you getting that answer?
solve, sir. Wait a minute.
Are you able to get now? Hello? Hello?
Yes, sir.
Are you able to get now?
No, sir. I will calculate, sir.
Where you are facing the problem?
Wait, sir.
Hello? Where you are facing the problem?
Sir, this is big problem. So I will study the question and analyzing and draw the diagram.
No, no. Which question you are saying?
Second question, sir. Next question. That question is understood, sir.
Oh, first question you have solved, na? Okay.
Yes, second question.
So this part, let me explain here.
Okay, sir.
So the sand deposit 12-meter thick overlies an impervious soil mass. So a vertical sheet pile penetrates 5 meters into the sand deposit. So this is the ground level. This is the impervious layer. This is 5 meters. And sheet pile, this is, uh, let me put it in a new slide. So this is impervious. This is 12 meters. And sheet pile is driven to 5 meters. Okay. Hello.
Yes, sir.
Are you able to get that?
Yes, sir.
So
Okay.
this is the sheet pile. So what they are saying, the water level on the upstream side is 3 meter and downstream side is 1 meter
Stream is
above.
1 meter above the
So
ground surface.
so this is
Length.
3.
Okay.
This will be 1. This is the ground surface. It will be 3 meters. It is 1 meter.
Yes,
Okay.
sir.
Now what they are saying. So the vertical and horizontal permeability for the sand deposit is 4 meter per day and 1 meter per day. What they have given, kx is equal to 4 meter per day,
X equals to 4 meter per day. KY is equals to 1 meter per day.
1 meter per day. Okay.
Yes, sir.
Now another thing what they have given. They have given there are 12 flow
NF
channels
and
and
ND.
24 NF and ND they have given. NF
NF
is
is equals to 12
12,
and ND is equals to 24.
ND is equal to 24. Now what they are asking to find, determine the seepage
See,
flow
seepage flow per day
per day. First is that point. Let us address that point. So Q is equal to
KH
KH
into
into
NF by ND.
NF by
ND.
ND. So K, how will you calculate? K is equal to K effective,
Root over KX into KY.
root over
KX into KY.
Kx into Ky.
So 2 meter per day.
It will be 2 meter per day.
Per day.
Head loss is 3 meters. See, sorry, 2 meters. H is 2.
Okay, sir.
How you are getting 2? This side it is 3, this side it
This
is 1,
side 1.
2 meters. So Q will be K is 2 into H is 2 into NF is 12,
So Q is equals to 2 meter per day.
24. This is
Okay,
2,
meter cube per day.
2 meter cube per day per
Oh.
meter square.
Or 2 meter square per day. Okay,
Ah,
okay.
anything. That usually that we don't use. You will use 2 meter cube per day. Okay.
Okay.
Now come to the second part. Calculate the exit gradient if the
Yes,
average length of last element is 0.9. Do you remember the previous problem which we solved?
yes, sir.
So
2 by 24. So
2 by
uh,
24,
the head difference 0.08.
which will be 1 by 12
So
by
0.
L, 1 by 12 into zero point 0.9.
So answer is 0.09. I exit
I exit will be 0.09.
09.
Okay.
Yes, sir.
So with this we will stop here today.
Okay, sir.
So since the time issue is there, maybe this last problem we will try to solve next week.
Oh,
Uh,
okay, sir. Sir, once see the last question. I tried.
okay, you can.
Okay, sir.
This slide will be uploaded,
Okay, okay, sir.
so you can see there and try it. And most probably, if based on the content of the next week, we will try to solve this question.
Okay, okay, sir.
Okay.
Okay.
So, but yeah, if you want, you can, for the time being, you can just take a photograph, or you wait for another 1 or 2 hours. It will be uploaded in your NPTEL
Okay, sir.
interface. So most probably, I will try to solve this question in the next week. So due to the time constraint, I am stopping here.
Okay, sir. Sir,
So yes,
it, geotechnical and this is pre NPTEL exam. So previous papers is there or not, sir? By
uh,
practice.
previous papers, I don't know, in NPTEL website, you have your account, right?
Yes, sir.
In that there might be some available resources, but we are not supposed to give any previous question papers and everything.
Okay, sir.
Okay.
Okay,
So
okay.
with this, we will conclude this session today.
Okay, sir.
So
Thank you, sir.
we will be meeting at the same time, Saturday, 5 o'clock, uh, next week, to solve some more problems. Okay. Thank you.
Okay, sir. Thank you so much, sir.